All right, so let's get started. Okay, we're going to be finishing up our discussion of chemical compounds today. Remember last week we introduced that most basic building block of matter, the atom, and then we started putting atoms together. We started bonding them together to create these chemical compounds. And we said that we're going to study two different types of chemical compounds, those held together with ionic bonds and those held together with covalent bonds. And actually all we did for the remainder of that first lecture was talk about our ionic compounds, all right? We first talked about how we would put these ionic compounds together, and we said that it was all about the charges, right? That's how we know how to put our formulas together correctly. How many cations and how many anions are going to depend on the charge of those ions. And then we talked about naming those compounds. So at the end, we were taking those chemical formulas and actually putting a name to those ionic compounds. All right, remember we had these two different types. Type 1 ionic compounds, where we can tell the charge on that cation just by looking at the periodic table. But then we also had these type 2 cations, which are our transition metals. And they require us to include what the charge is in the name of that ion, right? So for example, this isn't just an iron ion, it's an iron 2 ion because of that +2 charge, okay? To finish off our discussion of these ionic compounds, we got one more topic to go here. And today what we're going to start with are what are called our polyatomic ions. All right, and if we just want to pick this name apart here, polyatomic, what do we think that that means? All right, yeah, so the atomic means atom. What does that poly prefix mean? Many. So these are now many atom ions, or ions that are composed of more than one atom. All right, in fact, our polyatomic ions, what we're going to see is non-metal atoms covalently bonded together all right, these form molecules. All right, but what's special about these molecules is that they're actually ions, meaning they have a net charge. So they form molecules with a net charge, aka a charge not equal to 0. All right, so just some quick examples here of a poly. So what do I mean here? What's going on? All right, let's do an example. Okay, you might remember from Chem 1A, you would have been introduced to your first base of the semester, the hydroxide ion here. And so what we see are two nonmetals. Those nonmetals are covalently bonded together, so they're forming this compound. But this compound has a net charge of -1. All right, this is an example of what we call a hydroxide ion. We will be introduced to this in lab today. Not today, I'm sorry, this semester. All right, but importantly, our features here of our polyatomic ions, again, we have nonmetals, covalently bonded, and we have this net charge associated with it. Okay. Cool. So, truthfully, there are bajillions of polyatomic ions out there. All right. There are just a ton. It would be almost impossible to create a truly exhaustive list of all the different polyatomic ions that we see in nature. But there are a few of them that are super common, our most common polyatomic ions, and those are the ones that we just got to know this semester. All right. So what we're going to do is we're going to build our polyatomic ion cheat sheet. All right, this little cheat sheet of the polyatomic ions that we just got to know here. All right, the first one, the one we just introduced here, OH with a -1 charge. This is the hydroxide ion. Okay, and so by polyatomic ions that we just got to know, that means if I say hydroxide, you know I'm talking about OH with a -1 charge. You got to know the formula and the charge. Or if I give you this formula here, you know to name that as a hydroxide ion. All right, so these are things that we just have to have memorized here. Hydroxide, again, being famous because it is a strong base. Historically speaking, you can get hydroxide from certain rocks. It's how they were making soaps early on in our history. All right, another one that we got to know, NH4 with a plus charge here. So a polyatomic cation. This is what's called the ammonium ion. All right. Ammonium is going to be a little bit weird on this list as it's the only one that is a cation. It's the only one that has a that has a positive charge. All right. Now for the remainder of them, they all share some common features, and so I want to stack them next to one another. And so to introduce the remainder here, I'm going to make a little table, and y'all are just going to trust me for right now, and we're going to see in a second why this table is going to be helpful in terms of arranging these different ions here. All right, but we're going to make this table with these 4 rows and 3 columns. Okay? All right, so we're actually going to start in the middle here of our table. All right, again, these are our polyatomic ions, and what we're going to see is all of these have the same common feature where they end in ATE. They end in 8. All right, so the first one here is NO3 with a -1 charge. This is the nitrate ion. All right, or we could have CO3. This one has a -2 charge. This is a carbonate ion. All right, so a nitrate ion is pairing nitrogen with a bunch of oxygens. Our carbonate ion, carbon with a bunch of oxygens. If I tell you that there's also a sulfate ion, what do we think our nonmetal is here? Sulfur and a bunch of oxygens. So in this case, it's SO4 with a -2 charge. That is a sulfate ion. All right, and then our last one is PO4 with a -3 charge. This is a phosphate ion. Oops. Okay. So again, all of these have this same feature. They have this ending ATE. We can note that there are all these polyatomic ions that have some nonmetal bonded to a bunch of oxygens and creating an ion. So we have a net charge on there. All right. Importantly, in order to keep these straight, what are we going to have to know? We're going to have to remember how many oxygens we have and what our net charge is. Importantly, a nitrate ion always has 3 oxygens and a -1 charge. It's not like sometimes it's -2 or sometimes it's +1. This is a nitrate ion. All right. Once we got these 4 down, the remaining ones aren't too bad. These ones all have this ending ITE. All right, and we're going to use our same nonmetal, but this time we're going to decrease our number of oxygens by 1. So NO2 with a -1 charge, whereas NO3 with a -1 charge was nitrate, NO2 is nitrite. All right, so first of all, notice what happened to my number of oxygens. All right, so I decreased my oxygens by 1, going from 8 to 8. What happened to my charges? Stayed the same. All right, and that's going to be the same game that we're going to play for the rest of this here. With the one exception, it turns out there's no such thing as a carbonite ion. All right, but there is a sulfite ion. So who's brave? What do we think our formula for the sulfite ion is going to be? SO3 with a -2 charge. All right. Decrease our number of oxygens by 1. Charges stay the same. Okay. And likewise, we have a phosphite ion. That would be PO3 with a -3 charge. Okay. All right, so these 1, 2, 3, 4, 5, 6, 7, 8, 9 polyatomic ions are the ones that you just got to know. You have to have these memorized for this course. My expectation is I'm going to show you on an exam PO4, and you're going to know it's a phosphate, right? Again, in terms of what I mean by memorizing this, given this formula, can you tell me the name? Given the name, can you give me the formula? Okay? Now, memorization is a huge pain in the butt, so what we have to help you guys out is this polyatomic ions quiz that's built into Canvas for your homework. And so if you take it the first time, great. Take it with your notes open so you can get your full credit, but then you can go back in and practice. Just like every other assignment that you have in this course, you can go back and practice and it'll generate new problems for you. And the whole intention is that you close your notebook and you use that quiz to practice and memorize what those formulas and what those names are, right? So take it a whole bunch of times with your notebook closed, you'll have it in your brain, okay? All right, so these are the 9 we have to know. Why did I leave this other category here? Okay, I just want to make sure that we don't get these things that are pretty similarly sounding mixed up. Because last class we introduced a bunch of monatomic ions. What do I mean by monatomic ions? Single atom ions. All the anions that we introduced last class period were these monatomic ions, and we even made this little cheat sheet here. And what did our monatomic ions all end in? I, right? IDE. So since we got a bunch of similar sounding names here, let's just put them all next to each other. We're going to remind ourselves our monatomic all end in IDE. So we have a nitrate, a nitride, but last class we also learned about a nitride ion. All right, according to our periodic table, a nitride ion would have a charge of, who's got a periodic table in front of them? -3. All right, now likewise, we said that there wasn't actually a carbonide ion, okay, but we do have a sulfide and a phosphide ion. Everybody take a second to fill in those formulas. All right, sulfide, again, monatomic ion, so just sulfur out by itself. Sulfur living in oxygen family would form a charge of -2. Phosphorus all by itself in nitrogen's family, a charge of -3. Okay, so I just want to kind of make a column to stack these next to each other so we can remind ourselves and not get confused mixing up our ides, our eights, and our ites here. All right, so now we're going to take these polyatomic ions and kind of rewind back to what we were doing last class when we were putting formulas together and then naming them. All right, now the good news is it's the exact same game that we were playing before. There's really nothing new added on, except for our anions are these big, ugly clusters of ions as opposed to just being one atom all by themselves or one ion all by themselves. All right, so what do I mean by that? Let's say that I'm trying to put together an ionic compound that has sodium and nitrate. Well, when we put our formulas together, we said it's all about the charges. Yes, all about the charges, right? That's how we're going to make sure that we don't make a mistake putting these formulas together. So sodium, we look at our periodic table. Sodium has a charge of +1. And what about our nitrate? This one we just got to know. It's NO3-. All right, and the name of the game was the exact same as we were playing before. We're going to list our cation. We got to figure out how many we need. Then we're going to list our anion, figure out how many we need. All right, based on the charge of my anion, doing that swap and drop method, I know that I would need one of those sodium atoms, sodium ions rather. And how many nitrates am I going to need? Also just one, swap and drop that down. And just like before, if it's a 1, we're going to go ahead and omit it from the name. So my chemical formula here would be NaNO3. Put a box around it, final answer. Okay, so just like before, we're paying attention to the charges of our cations and our anions. We're doing that swap and drop to make sure that we have the same amount of positive and negative charge. All right, we would reduce it all the way if we needed to do that step. All right, and then we're going to name these. We said last class that this thing here, what would we call this cation? Just the sodium ion, right? Nothing crazy. And we just went over this. Whoops, my 3 got deleted here on accident. We just went over this here. What's the name of this thing? The nitrate ion. And remember, when we put our compound names together, it's just cation, then anion, and you drop that word ion. So this would be sodium nitrate. All right, same game as we were playing before. It's just now our anions are these clusters of atoms here, our polyatomic ions. All right, so let's do K something. And CO3 something. All right, build this compound formula and then name it for me. All right, potassium has that +1 charge living in that first family. What do we call that first family? Our alkali metals, right? So all of our alkali metals form that +1 charge when they make irons. And carbonate, we just got to know, has a -2 charge. So then how many potassiums am I going to need in this formula? My 2, right? Do my swap and drop down here. So K2. And how many carbonates am I going to need? Just 1, so that's good as it is. So K2CO3 is my formula here. Okay? And then how are we going to name this thing? This ion is the potassium ion. This is carbonate. So our name here is just potassium carbonate. All right? So now let's do another one here. I want to make one with Cu plus 3 and SO4 minus 2. All right. So how many coppers, Cus, am I going to need? 2, right? This number, drop it down. How many sulfates am I going to need? 3. All right, so we haven't seen this before. How do we indicate that we have more than one of these polyatomic ions? We need 3 of them. Well, we need to indicate that we need 3, not just sulfurs and not just oxygens, but that SO4 package, right? That sulfate is a package deal, SO4. And so in order to indicate that we need 3 of them, we're going to put it in parentheses. All right, and we're just going to make a note. We're going to use our parentheses. Whoops. When we have more than one of our polyatomic ions. If there's just one of them, like in the first 2 examples, we didn't bother to put parentheses. As soon as we have more than one of them, we're going to put them in parentheses. Okay? So here we go. All right, everybody take a second and name this compound for me. All right, and I have a feeling I'm going to be able to stump a few people here with our naming of this compound. All right? Because this ion right here has what name? Our cation. Copper, but copper what? Copper 3. This is our copper 3 ion and our sulfate ion. So my answer here is copper 3 sulfate. All right, why the heck is it copper 3 if I only have 2 coppers? Because it corresponds to the charge on that ion, right? That's what those Roman numerals in our name mean. The charge on that ion. It was supposed to have this little blue color. Okay. All right, and then the last one, let's just, again, we're going to use our parentheses. Last one, let's use that polyatomic cation, NH4 plus, and PO43 minus. So NH4, how many do I need? PO4, how many do I need? So how many of those NH4s do I need? I need a total of 3. And since I'm indicating that I have more than one of our polyatomic ions, I'm going to throw it in parentheses. How many phosphates do I need? Just the 1, so I'm cool as it is. Boom. And what would be the name of this molecule? Ammonium phosphate. Cool. All right, so now last complication for our ionic compounds are introducing these polyatomic ions that we got to know here. All right. Again, there are truthfully many, many more polyatomic ions out there in the world. However, these are going to be the most common ones that we're going to encounter. So these are the ones that I need you to be able to sight recognize. Cool. All right, so now we're going to switch gears. Finally talk about that other type of compound, our covalent compounds. All right. So first of all, synonymous with covalent compound is the term molecule. All right, a molecule is a covalent compound. Every once in a blue moon, you'll hear a ionic compound incorrectly referred to as a molecule, but strictly speaking, when we talk about molecules, they're necessarily covalently bonded atoms. Okay, let's just note, all right, we talked about covalent bonds. If you're a covalent compound or a molecule, that simply means that you're held together by covalent bonds. All right, and what was that word that I told you I wanted to have synonymous in your brain with covalent bonding? What's happening to the electrons in a covalent bond? They're being shared between those bonded atoms. Yes, when you hear covalent, you need to think a shared pair of electrons. And what type of elements do we see covalently bonded together? Are nonmetals, right? All nonmetals are what we're talking about here in these covalent compounds. All right, when we were talking about ionic compounds, we kind of had a lot of groundwork that we had to do in order to understand how these formulas were put together and how to name them. Covalent compounds are a little bit more straightforward, so we're just going to jump right in to our formulas and naming. All right. For ionic compounds, again, we had this whole logic, and that's because it was all about the charges, right? Well, in covalent compounds, there aren't charges anymore. It would be incorrect to refer to a covalent bond as involving charges. That's not how it works, right? We don't have positively charged ions or negatively charged ions anymore. Instead, these atoms are held together by those shared pair of electrons. And we don't have as many rules around it, at least at this point in your chemistry career, as to how we can put those compounds together. So one big difference is that our formulas for our ionic compound, or rather for our covalent compounds, all right, these formulas can be, I guess, just to be good, I mean, our chemical formulas can have any number of each element. All right, when we were talking about putting an ionic compound like sodium and chloride together, the only way we could do it was one sodium ion and one chloride ion. All right, for our covalent compounds, we're not going to have those same rules on what those subscripts could be. They could be any number. All right, at least as far as y'all are concerned at this point in your chemistry career, truly there are some rules that we'll learn further down the road about what molecules actually exist and what don't. But for right now, if I give you a formula for a covalent compound, you're just going to trust me and be like, yep, that thing exists, all right? Because there's not the same rules that we see. So as an example, we have CO2. What is this molecule? Carbon dioxide. All right, your body takes a sugar and combines it with oxygen to create energy, and we exhale carbon dioxide. And then we have its much more toxic cousin, just CO. What's that? carbon monoxide, right? So there's no rule as to how many oxygens there has to be relative to our number of carbons. We have one example with 1, we have another example with 2, and these are both perfectly legit molecules. Okay. Another example, just to kind of put it down here, would be N2O4. This isn't one that I think that you guys have any sort of like pop culture knowledge about here. But importantly, this illustrates a big difference between what's allowed with covalent compounds that's not allowed with ionic compounds. Remember, with ionic compounds, our subscripts could not share any common factors. We don't have that rule with covalent compounds. This is perfectly legal here, right? So again, these subscripts can be any number we want them to. We don't have the same rules that we do with ionic compounds. If I'm going to name this thing here, again, this isn't one that I would expect you to know, but we're going to know it here. This is dinitrogen tetraoxide. All right? And I think that these examples here are sort of great to work off of to make our rules for naming these compounds. All right? So let's just jump right into rules for naming covalent compounds, or let's just call them molecules. All right? So first thing that we're going to notice right off the bat in all these examples that we didn't see in any of our ionic compounds are these prefixes. Because these chemical formulas can be anything we want them to be, because they can be any number, we have to build what that number is into the name when we're referring to a specific molecule. Right? So we're going to distinguish between these two molecules that contain carbon and oxygen by calling this one carbon dioxide. What does the di mean? That there's 2 of them, versus carbon monoxide. What does the mon mean? There's only 1 of them, right? So we've built into the name here how many of each element we have present. Because again, those numbers could be anything. All right? So number 1, we're going to note we're going to use these prefixes to indicate the number of each element. All right, and I'm going to be dead honest with you. I'm not a language guy. These are either Latin or Greek, but I couldn't tell you which ones. But we're going to learn these prefixes that indicate the number of atoms in our ionic compounds. So we're going to make a little cheat sheet here. We're going to have the number of each atom, and then the prefix that we use. All right, and we're going to go all the way up to 10 here. Okay. So what's our prefix for 1? We saw an example previously. Mono. And 2, that was di. 3, tri. And 4, we saw an example of before. This is tetra. And then they start to sound really familiar from our geometry class. 5 is penta. 6 would be hexa. I don't know where septa comes from, but we don't really use it in chemistry. Instead, we use whatever the other language derivation is for 7, which is hepta. All right, and you see this all over the place in chemistry. We use hept or hepta for that to indicate 7 of something. 8, like a stop sign, would be a octagon. 9, you might not know, 9 and 10. 9 is nana, and 10 is deca. And truthfully, they keep going and going and going, but this is just fine for our purposes. Okay? One thing that we want to note about these prefixes is in our 3 examples here, sometimes we see them, sometimes we don't, all right? So first of all, let's note carbon dioxide, but there's no prefix on the carbon. Carbon monoxide, again, no prefix on the carbon. But then over here we have dinitrogen tetraoxide. Importantly, we're only going to stick one of those prefixes on the first element if there's more than one of them. Okay? I think it's most helpful if you can just remember these 2 examples. You can kind of flesh out a lot of the rules for naming ionic compounds. Just pull up or rather covalent compounds. Just pull up these 2 examples that you have this intuitive knowledge of, and it's very helpful. All right? So we're just going to note we omit on our first element if that number is 1, but we always include it on the second element. All right, last thing we want to note from these examples above. Here we have the element carbon, and how did we refer to it in its name? Carbon. Nothing special. Here we had nitrogen in our name, or in our formula. How do we refer to it in our name? Nitrogen, just like it said on the periodic table, right? So the first element, we don't do anything special to. We just grab it straight from the periodic table. But what about the second element in our formula? What do we do to that one? We added the prefix. We always add the prefix. But what else do we add to the end, to the suffix? That IDE. Just like we saw with our ionic compounds, note that always my second element ends in IDE. All right? So in terms of our element names, all right, our first element, just like on the periodic table, and our second element gets that IDE ending. What's up?
So will it be wrong if we capitalize the first letter of the prefix? So like all the letters are small.
Yeah, so this is a good question. Compounds, elements, all those things are not considered proper nouns. So just like if you were referring to a table or something like that, you would capitalize it at the beginning of the sentence, but that's it. If you were using it in conversation, it would not be capitalized like the name of a city or your name would, a proper noun. So technically speaking, our elements should be lowercase unless it's the first word in a sentence. On your homework, it'll accept either. All right, but just FYI, they are not considered proper nouns. Cool. All right, so what we need to be able to do with this, exactly like we were doing for ionic compounds, what we want to do is to be able to convert from the name to the formula or the formula to the name. All right, so let's just practice converting from name to formula or back to the name. Okay, so just like before, I'm going to put down if I put down a formula, you're going to name it for me. If I put down a name, you're going to give me the formula. All right? All right, OF2, what do we got? Oxygen. Don't do anything to the element name. I also don't include any prefix because there's only one of them. Oxygen difluoride. Right, my second element gets that IDE ending. One thing that I just want to say, if you're getting stuck in these fluorine compounds, a lot of people try to misspell fluorine fluorine. F-L-O-U, fluorine is F-L-U-O, all right? So just a really easy spelling mistake to watch out for. All right, what about this one? Tetraphosphorus, because we got 4 of them. Tetraphosphorus decaoxide, awesome. All right. Going from name to formula for covalent compounds is kind of best case scenario because it really spells out for you how much you need for each one of them. All right, so my formula here should be S, how many? 3 Cl5. Right, my trisulfur telling me there's 3 of them. My pentachloride telling me there's 5 of them. And then this last one, I think if I'm going to trip anybody up, I think it might be on this last one here. All right, so my first word in my name is diselenium. All right, but what's my second word? Mononitride. Awesome, right? Remember, we can't omit the prefix on the second element, so this is mononitride. Cool. All right, and again, for right now, like I'm going to be dead honest, this is completely made up here. For right now, you're just trusting me if I give you one of these chemical formulas that this thing exists. We will talk later on, actually towards the end of the course, when we're actually starting to put molecules together, looking at what we call their Lewis structures. We'll see what formulas are allowed and that certain formulas aren't allowed, but we're not there yet, right? So as far as you're concerned at this point of the course, whatever numbers I put here, you're going to be like, yep, sounds good, okay? The other thing that I just want to note is what we know how to name are these very simple binary covalent compounds that have exactly 2 different elements. There's way more covalent compounds in the world out there, and they have much more complicated nomenclature schemes, right? So we haven't learned how to name everything yet. We've learned how to name a subset of these covalent compounds that contain just 2 elements. Cool. All right. Last thing we're going to do, we're going to switch gears a little bit. We've been sort of avoiding some math in this chapter up until this point, and I know everybody's super disappointed. So let's finish this off with a quantitative discussion here of what's called average atomic mass. Okay, so if we go to our periodic table here, we look at one of these values. So for example, lithium, one of our entries on our table here is this 6.941 number, all right? And this corresponds to lithium's what? What do we call these numbers? This was the atomic mass of lithium. All right, or if we're being really good, it's the average atomic mass. Okay, so what do I mean by that? So first of all, if I'm holding a lithium atom in my hand, how many protons does it have? 3, right? And that's because the atomic number of lithium is 3. In order to be lithium, you got to have 3 protons. Okay, how many neutrons does that atom have? Trick question, right? You don't know. It could have 3, it could have 4, it could have 2. Those are all different isotopes of that lithium, All right, so each tile on our periodic table really represents a collection of different isotopes that corresponds to that atom. And where is all the mass of an atom located? In its nucleus, with its protons and its neutrons, right? So different isotopes have different masses. And so what we see on this periodic table, it's not just the mass of one of those isotopes, it's an average of all those lithium isotopes. So if I took a scoop of lithium, I would have a mixture of all of those lithium isotopes, and on average, the mass of those atoms is that 6.941. All right, so this mass that we see on our periodic table is an average of all the isotopes that make up that lithium element. All right, so let's just kind of summarize, or rather recap here. Okay. So as we said, each element is actually a collection of different isotopes. Okay. We don't have any pre-notion of how many isotopes there are. Like maximally there's a handful, and they tend to be much fewer depending on how smaller elements have fewer isotopes than larger elements. All right, but regardless, they're all a collection of different isotopes, and each isotope has a different mass. All right. The atomic mass on our periodic table is what's called a weighted average of all of an element's isotopes. All right, and this weighted average calculation is what we're going to learn how to do here. All right, so we can kind of just header this if we want. We're going to learn how to calculate average atomic mass. Or what I'm going to simply refer to from here on out as AAM. Okay, and I'm just going to put a sample problem down here. So we had pointed out lithium. All right, I'm going to tell you that lithium is composed of only 2 isotopes. All right, that is lithium-6 and lithium-7. All right, so it turns out that all the lithium atoms in the world either have 3 neutrons or 4 neutrons. Okay, and I'm going to give you this data table here. I'm going to tell you for each one of these isotopes, I'm going to give you the atomic mass of that isotope in AMU, and I'm going to give you what we call the percent abundance. All right, before we go on here, what do I mean by percent abundance? How much is of each? Yep, so for example, oxygen, or rather carbon, is composed of 2 isotopes. Well, one of those isotopes, carbon-12, is present in a much greater quantity than the other one, right? There's not a 50-50 mix of all these different isotopes. They exist in a different percentage out there in nature. All right, so first, lithium-6 and lithium-7. These are our two isotopes. I'm going to tell you the atomic mass of lithium-6 is 6.0151 AMU, and lithium-7 is 7.0160. All right, notice how the atomic mass of an isotope is very close to its mass number, but it's not identical. All right, this is if we actually busted out our supersensitive balance and measured the mass of that atom, what it would be. It's pretty close to just the sum of its protons and its neutrons, but it's not exact. All right, and I'm going to tell you that our lithium-6 is present in 7.59%. All right, so my first question, how much lithium-7 is there?
8.
All right, so let's, whoops. Okay, let's first ask how much lithium-7, or rather, what is the percent abundance of lithium-7? Anybody got any ideas? Cool. All right, so there's this key piece of information in the above problem, which is that there's only two isotopes of lithium. All the lithium in the world is going to be divided up into these two buckets here, which means that the sum of these two boxes must equal what? 100%. That'd be 100% of all lithium falls into one of these two buckets, right? So that means let's use a variable instead of a question mark. I'll make this an X. So what I know, because there are only these two isotopes, is that my 7.59% of my lithium-1, all right, we can even do this symbolically, or my lithium-6 rather, lithium-6 plus lithium-7 has to equal 100. So 7.59 plus X must be equal to 100. If I rearrange this, I get X is equal to 100 minus that 7.59, or 92 and some change. 9241? Is that right? Sounds right. Yeah, 9241. Okay, cool. So now we've completed our data table here. We know we got 92.41% of that lithium-7. So which isotope if we get a scoop of lithium, which isotope are we going to have more of? Lithium-7, right? 92% of all lithium is lithium-7. The rest of them is that lithium-6. Okay, so now we want to know what is the average atomic mass . Okay, and for this we're going to have to do a weighted average. All right, an average where we have to account for these weightings here, right? The different percentage abundance of each of these isotopes. I can't just take my straight average where I add these two up and divide it by 2, because that would weight this isotope just as equally as this isotope. And there's way fewer of the lithium-6 isotope. So we got to incorporate these percentages into our averaging here. Again, what we call a weighted average. Some of you have probably taken classes where they lock in percent, like exams are 15% of the course or something. That means your grade at the end of the semester is calculated using one of these weighted averages here, right? Where that percentage is taken into account. All right, so how do we do this? We're going to take our average atomic mass. This is going to be the mass of isotope 1 multiplied by that percent abundance of isotope 1. Although if we're going to use this percentage in a math here, we got to convert it to a fraction by dividing by 100. All right, we like percentages as humans. They kind of make us feel good and we have an easier time understanding them. But if you're going to use it in a math, you always got to divide by 100, right? Turn it into a fraction. And then we're simply just going to take the mass of that second isotope, multiply it by the percent abundance of that second isotope, again, convert it into a fraction by dividing it by 100. All right, so given our data table above, I want everybody to take a second and calculate lithium's average atomic mass. All right, now I have some good news for y'all with regard to sig figs, which is that they're such a pain in the butt that for these types of problems, I'm just going to tell you round to 3 decimal places. All right, you'll see a little hint pop up on your homework telling you how many digits to expect, or rather how many digits to enter for your answers. Okay? So our average atomic mass of lithium is going to be that 6.0151, the mass of lithium-6, times its percent abundance divided by 100, plus the mass of lithium-7 times its percent abundance divided by 100. And the calculator spits out 6.940. All right, what would our units be? AMU, right? Our mass is up here, we're in AMU. So our mass at the end is going to be in AMU. All right, and what we did was just calculate the average atomic mass given the different lithium isotopes, their masses, and their percent abundances. All right? And how can we check whether this number is reasonable? The periodic table, because remember, what's on the periodic table is the average atomic mass of these elements. So our number better be close to the average atomic mass of these elements, right? It might not be exact because we get data from different sources. Our data isn't exactly perfect. But if we look on, so this is what we just calculated. right, if we look on our periodic table, we get 6.941 AMU. All right, not exact, but very close. Okay, and again, just to hammer home here, that value that we see on the periodic table, it's this weighted average of all of an element's isotopes, right? That tile represents all the atoms that have that number of protons, but they can have a different number of neutrons. We got to average those together. Cool. All right, I'm gonna call it there. I'm gonna end things a little bit early here.